All right, so we're going to look at fluids here, and first and most common misconception is the term fluids, or the term fluid. And a lot of people assume when you hear like fluid mechanics, you're talking about a liquid of some sort. Fluids make up two of the states of matter, both gas and liquid. Okay, so just to start to give you a heads up about the name of this. This is called fluids in buoyant force, but any gas or any liquid is a fluid. Okay, and a fluid is something where the molecules can easily pass by one another. For example, the lattice structure that makes up these solids here, the molecules cannot be easily rearranged. But if I have a cup of water, which I had a moment ago, okay, if I have a glass of water and I just rotate the glass, I see the fluid, the liquid in this case, but the fluid in general, start to like change and move past itself. If you start to spin it, you'll see like a little whirlpool. But the idea is that the molecules can easily move past one another in a fluid. Okay, so that is true for both a gas and a liquid. So a gas and a liquid is considered to be a fluid. So that's the first thing we're going to do is define a fluid there. We'll talk about liquids, gases, we'll talk about density, the buoyant force, and then talk about floating versus sinking. Okay, so that first definition is what I just stated right there. The second and third definition are just being more specific about liquids and gases. You can read it, but based on what you know, what's the difference between a gas and a liquid? The difference between a gas and a liquid.
The arrangement of particles and how close they are, making change in density of it.
That's one, good. That's one possibility, good. So the density or the arrangement of the particles, specifically for a gas, they're more spread out. For a liquid, they're more condensed. Good. What else?
Just one is at room temperature when it's gaseous is like tangible. It's tangible.
Yes, tangible.
No, you're wrong.
Well, you can touch it.
Yeah, but you don't feel it.
You don't feel that.
If there was like a cold air or a cold gas coming out of your exhaust pipe.
Jack, you didn't teach me that.
Jack, Jack, John, you're on the right track. Be more specific though. You said one is tangible, one is not. What do you mean? Give me more. Tangible might not be the word you're looking for. I think you're on the right track. You're getting there. You're hinting towards it. What's another difference between a gas and a liquid? They both move rather easily. Gas is probably easier than a liquid.
Well, it's kind of said though. Yeah, I know, it's always actually out there.
That's fine. So state the difference. That'll get.
Liquid always takes the shape of its container.
Yeah, that's the big difference. The shape of the container the liquid takes on. The liquid itself usually feels gravity holding it down, so it wants to take the shape of the container that it's in. Whereas a gas is, well, it depends on the gas, actually, I should say. Some gases, when you blow on like the floor, ever go like, what is it called? I forget the actual gas, but you know like a fog machine? You see the fog on the ground, like a haunted house or something? You'll see like a layer of fog on the ground from fog machines. Well, I forget what the gas is, but if the gas is more dense than air, you'll actually see the gas lower, and it might stay along the ground. But most gases, they have no set shape. Even if it's in a closed container, it will remain in shape. Like for example, helium filling up a balloon, right? It takes on that, I guess you'd say, an ellipsoidal shape. It's not a sphere. Okay, it's like an ellipsoid. But the minute you puncture the balloon, what will happen? It pops. But what will happen to the gas? Yeah, the gas disperses itself, spreads across the room. Okay, the balloon reforms back into this little small balloon. Now I'm not talking about like the balloons, but that are made of that like metal, metallic kind of. You know what I mean? Like the happy birthday balloons, not those. A normal balloon that you would blow up. Okay, the gas escapes. It leaves the balloon. It takes on the shape of no container anymore. It's kind of just being out in the atmosphere. So the biggest difference here is that a liquid will take on the shape of the container. Okay, a liquid will take on the shape of a container. This is a really picture, but I thought it was kind of funny. So I saw this on Facebook like 2 years ago, but it just gives you an idea of, what a liquid is again. A liquid takes the shape of the container. So the joke is that the cat is a liquid because it's taking on the shape of the container. It's really not, obviously. Okay, but the definition of a liquid, by its definition, you could say that, except for the fact that another part of the definition of a liquid would be that the molecules can easily flow past one another, whereas a cat is a solid. It's clearly not flowing past itself. Okay. Now, density, you've heard the term density, but when you hear the term density in science classes, usually you hear mass density, and you don't realize it. But when you hear density, if I say what's density, most people say mass over volume. Mass over volume. Okay, that's mass density. We're going to see in that second statement. But density as a whole, we need to recognize that density can take on many different situations. So, for example, if you're looking at what's called the population density, what are you really looking at? What's population density? The people per square mile, or per square area, per unit area. People per unit area. That's what mass population density would be. What other types of densities? There's an infinite amount, really. Density is a generic term. Give me another example of something that's measured by its density. A tire? What do you mean?
Like a race car.
Okay, give me more. What about it?
The amount of gas they have in the tires, directly correlates to how they use drive.
Yeah, so if you think about the amount of gas in a tire, it's really a pressure, but that's density. Pressure is technically density. All right, think about pounds per square inch. It's a concentration of molecules or of a substance. So density is the quantity of a substance or entity in a given amount of space, really. In a given amount of space. Sometimes even in a given time period we talk about. And then you're talking about density that's temporal. It's a function of time. So density itself is a general thing having to do with concentration. So in chemistry, you might have looked at figuring out, I don't know, say you want to make a 20% solution of an acid, and you're given a 22% solution and a 10% solution, and you have to mix them in a certain proportion so that the final solution is 22% acidic. Well, that's the concentration of acid. 22% means 22 parts out of 100. 22 parts of that liquid are acid out of the full 100. If you're looking at a virus or a bacterial that can spread through the air, you look at parts per million, ppm, parts per million. Okay? If you're looking at some sort of environmental byproduct or waste, okay, so say there's a production plant and the facility itself produces X amount of toxic waste. Well, you might have that as a density. The density might be a rating of, gallons of toxic waste per some rate, I don't know, per year, or per square foot of the amount of the size of the building or the manufacturing plant. But these are all densities. Density is just a rating or a concentration. Okay, we're specifically going to talk about mass density here, but it's important to understand that density itself is a generic term. Okay, so mass density, as you know, is mass over volume. Okay, mass over volume. What does the word incompressible mean? Incompressible. What does that term mean? If you don't know, use context clues. Dirks.
That you can't decrease the volume.
You cannot change or decrease, I'm glad you didn't use the compress because it's an easy way to get it out there. You cannot decrease the volume of something that is incompressible. So for example, if I have a balloon, I could technically decrease the volume. If I decrease it too much, what will happen in the balloon? It'll pop, because the pressure goes up as volume goes down. You know that PV equals nRT. Remember the gas laws from chemistry? So as a result, incompressible things cannot be compressed. I know it's obviously using the same word, but cannot have its volume reduced, okay, as Dirks mentioned. So we could simply say that solids are definitely incompressible. Solids are incompressible. Gases are not incompressible, which is kind of a double negative, meaning they are compressible. Liquids could be both, but we assume liquids are not compressible, or they're incompressible. Okay, so solids are definitely incompressible. We assume liquids are incompressible, even though they can technically be both, depending on the liquid. And gases are assumed to be compressible. Yeah?
If you had a solid, there's no way you could crush it to, like,
If you had an actual solid object, no. I mean, it depends on the object, though. Like, for example, if you have this box right here and it's empty, this is not a solid object, really, right? It's got air inside of it, so you could compress it. Cardboard is not really a solid. It's a porous solid, like a sponge. A sponge is, I mean, I know a sponge is technically solid, but you know what I mean by solid? A fixed solid. So a material that's malleable, obviously, like a sponge would be a good example. A sponge clearly is compressible. You can squeeze it into a little ball, especially once it gets wet and malleable. So that's a little bit different. I'm talking about when I say solid, I mean a solid material, like a naturally occurring solid element.
Like a diamond.
Yes, exactly.
So even if you apply like all the pressure in the world, you couldn't crush a diamond?
Some you can. I mean, like that's how you get a diamond. You take coal and over years and years and years, it's compressed more and more and more, and a diamond is the result of it, actually. So non-man-made diamonds, they take, I think it's, what's coal? It's carbon something, some sort of carbon. I don't know, but they take it and they actually compress it down to actually get a diamond. So what we're saying here, guys, is we're talking about solid objects, okay? Solid objects like this, not objects that are malleable. And I know it's a generic term, but let's say solids are incompressible. Okay, yes, some solids can be compressed. Okay, again, liquids we're assuming to be incompressible, even though many liquids can be compressed. But for flow rates, we assume that liquids are what are called Newtonian, and Newtonian liquids are incompressible. Okay, really simple math. Okay, really simple math. Figure this one out. We have a density given.
So what's your unit
For what? For volume, cubic meters. Because remember, volume is a length times a width times a height. Meter times meter times meter. It's cubic meters. The density of a meteorite is 1,250 kilograms per cubic meter. The mass is 250 kilograms. What would the volume be? What volume would the object displace if it was submerged in a tank of water? So what is the volume of the object, really? Let's talk about this. So we've got a tank of water. Now, what happens is this. You drop the object in the water level does what? It rises up to maybe up here now, that dashed line right there. Now, the amount of fluid that is risen is equal to the volume of the object. Anybody know who discovered that before I get into that in the next few slides? Sorry, look ahead. Right, very good, Jack. It's Archimedes. Archimedes' principle, okay? The idea, I mean, the whole, saying was that he got in the bathtub, recognized that the water flew out over the side, so displacement of a fluid is equal to the volume of the object that's doing the displacement. So if you take a solid object, something that can't absorb water, and you place it into a fluid, the amount that the fluid rises, the volume that it rises by, is equal to the volume of the object. And you know this. You obviously see this all the time. Take an ice cube, put it in a cup, what happens? Water goes up. Gradually that ice cube melts, and believe it or not, it actually decreases in volume. Because water is one of those interesting ones because of the hydrogen bond. Okay? So, in this case, if we want to find the volume of the amount of fluid that's been displaced, we want to figure out what is the volume of the actual object. So use your mass density here to figure this out. That symbol right there, what was that called? I went over it once real quick in this class. Anyone remember that? I mentioned it, like I literally mentioned it for like a second during one class. It's called rho, R-H-O. Okay, and rho is defined as mass over volume. This is density. Okay? So we're looking for volume, so solve for V. What do you get? 1/5 or 0.2? Either one.
Oh, I thought you were asking.
Oh, no, I'm saying they're the same thing. 1/5 or 0.2.
It's 1/5.
Notice your units of kilograms cancel. Meters cubed are in the denominator of a denominator, which bump those units up to the numerator, giving us units of meters cubed. And again, that's our volume. Now, what is volume usually measured in the United States? What is it? Gallons. What is it traditionally measured? I should say, what is fluid volume? What is it measured in other countries? Liters. It's liters and gallons are the main two you want to know. Okay, fluid ounces also, yes. But fluid ounces can be converted to gallons also. Ready? In case you want to know, you can jot these down. Not that you have to know them, but you should know them for everyday life. 8 ounces in a cup is a fluid ounces. 8 fluid ounces in a cup. 16 fluid ounces in a pint. I'm just doubling. 32 fluid ounces in a quart. 64 fluid ounces in a half gallon. 128 fluid ounces in a gallon. Okay, those are your conversions for ounces to gallons. In liters, it's great because it's liters or it's milliliters. So your units, you use prefixes again. So if you have 500 milliliters, it's a half of a liter. If you like saying you have 500 millimeters, well, 500 millimeters is half of a liter. Okay? Easy enough for this kind of a problem? This is like simple math for this section. The math we're going to do in a moment is a lot more complex than this. Okay, this is definitely a heavy math section, just so you know. This chapter in general is heavy math. All right, so let's talk about buoyant force. Let's talk about buoyant force. What is buoyancy? You can read the definition, but tell me what buoyancy is to you.
Force that.
So about floats, the force,
I was going to say
the ability to float. Like a buoy, good. Hence buoyancy. Buoy, buoyancy. Makes sense? No, that does. So, what is it really like, though? I mean, you can look at the definition, but what is it doing?
it's a release.
Not a release.
It's like halfway displacement.
Okay, if you're like halfway in the water, but I'm asking the buoyant force, what does it do? What does it really provide? Some sort of what? What's the term? For every action, there's it's a reactive force. Okay? It's a reactive force. Yeah, that's what I was saying. You can look at that if you want. It's a reactive force, and it responds to the force downward, but it really is based on how much of the fluid is displaced. So if we look at the exact definition here, okay, let's look at the exact definition. We're looking at a fluid's force that's exerted upward on a submerged or floating object. Okay, on a submerged or floating object. Now, when you're in the pool, what does it feel like? What does it feel like when you're in the pool? You feel lighter, right? You could be floating, yeah. You could be doing like the dead man's float on your back and being able to maintain a floating position. Now, if you go down to the bottom of the pool, right? Say you're in the deep end, you dive down to the bottom, and you're holding your breath. What's your body going to naturally start to do? Just have to rise back up. Okay, it's going to rise back up. How would you stay at the bottom?
Blow out all the air.
Blow out all the air. So we'll talk about that in a little while, how that relates to density, and many of you probably can figure that out already. But your apparent weight is what's happening in the pool. So you might weigh, hypothetically, let's pick a number of 150. When you're in the pool, you might only feel like you weigh only like 70 pounds. That's why a lot of people do like medical rehab when they have like physical therapy for an injured muscle or something underwater. You'll hear that a lot. If you have a pool, like my own personal experience, I hurt my hamstring pretty badly about 3 years ago. And the first thing that my friend's a physical therapist, the first thing he told me, because it was in the summer, was he's like, just do laps in the pool. He goes, even if you have trouble walking, just walk slowly across the pool, because your body naturally will start to heal at a slower rate, and that's what you want to do. That's what physical therapy is. Anybody ever gone to physical therapy? What do? They start with like bands, and they're really light. And then you build up muscles, and you build up more muscles. And usually you strengthen the supporting muscles around the muscle that you've injured. So you start in a pool because of the apparent weight that you feel. You don't feel as heavy, so your muscles don't have to do as much work. So instead of lifting like 100 pounds as you're walking, you might only be moving like 70 pounds or feel like you're only moving like 40 pounds, depending on it. So the idea here of apparent weight is the difference, really. The difference between what?
Your actual weight, you feel it.
your actual weight,
And the weight of what you're at.
close, that was almost there. The apparent weight is really the difference between your actual weight,
And what you weigh inside the
that is, what you weigh inside the pool is the apparent weight.
How you feeling?
Damn.
So it's the difference between your weight, what forces? Your weight,
Oh, and the force, that's keeping force now?
yes, that's right. Say it again.
I don't know how to pronounce that.
You were right.
Buoyant?
Yep.
Force?
Buoyant force, very good. The difference between gravitational force, your weight, and the buoyant force is really the apparent weight. So if I weigh 150 pounds and buoyancy is pushing up with 20 pounds, what do I feel like I weigh? 130 pounds, 130 pounds, right? I mean, it makes sense logically. So if I weigh a certain amount and buoyancy counteracts that, it's like saying I don't really weigh that much. It's apparently what I weigh, the apparent weight. Okay, the difference. It's like the net force acting on the object vertically. That's what apparent weight really is. Assuming the object is not accelerating. Okay, so let's see this real quick in a diagram. We've got FG acting down. We've got FB acting up. What does the B stand for again? Buoyancy. Let's put this bad boy underwater here. I know I'm a weirdo, it's okay. So the difference between the gravitational force and the buoyant force is physically what you're seeing. Well, all that is the sum of the forces in the y direction. If this object is at rest, sum of the forces is 0, there's no acceleration. So you'd get FB minus FG. Okay, this, in this case, if it's floating, is equal to 0 because it's not moving. So as a result, these two things will be equal to one another for an object that's floating. And we'll talk more about that as we go on. But the idea of apparent weight needs to be clear. Because I think last year a lot of people didn't seem to know what that was mathematically. They understood it tangibly, right? But mathematically, your apparent weight is the difference between these two things. If you're not floating, okay, if it's at the bottom here, if it's at the bottom, what does that mean?
Your apparent weight is greater. Oh, never mind.
If the object is at the bottom, what does it mean?
The force is greater?
What force is greater?
The buoyant force?
What is it?
That's pulling you up, isn't it?
It's like normal force.
Say it again, Julia.
Gravitational.
Gravitational force is greater if you're at the bottom.
What?
The buoyant force pushes you up. Buoyant force pushes you up. Gravitational force pulls you down. If you're at the bottom of the pool, if you're at the bottom, which means sinks, it means that gravity is more than buoyancy. Gravity is more than buoyancy. It means that the object is more dense than water.
Oh.
So what is? Think about it. How does something
So
sink?
what's the six, yeah.
Things that sink are more dense than water. So if something is more dense than water, it sinks, the weight of it is greater than the buoyant force pushing back up. That's all that's happening. A boat is very, very, very low density because there's a lot of air in a boat. There's a lot of volume. And density is mass over volume. So a boat's objective is to maximize its volume. If you have a boat that gets bigger and bigger and bigger, the boat itself becomes less and less and less dense, therefore it floats. Okay, keep that in mind. We're going to do a bit of a challenge as our lab for this chapter. It's a competition in class. And that would be very useful, that theme, or that idea. Yeah, that's actually what we're going to be doing. We're going to see who can construct the boat that holds the most pennies. That's going to be the objective.
What is the symbol next to ice?
Well, we'll see how easy it is. What?
What's the symbol next to ice?
Summation, the sum of the forces. Remember that squiggly E? It's called sigma.
That is a Y, right?
Yeah.
What is that?
The other one's G, FB minus FG. The other up here is a Y. The Y direction, vertical. Like X and Y, right? X and Y. Ready, but let's take a look. Shh. Let's take a look. Mullen looked ahead and saw Archimedes' principle here on this one. He was able to recognize that when this object is lowered into the water pours out the spout. This is perfectly set up for a scientific experiment, so that the water level is exactly level with the spout opening. As soon as the object is submerged, even partially, water comes out. You can barely see it. Look at your notes, it's probably more clear. Up here, you can't see it that well. Once it's fully submerged, all the water from the volume equal to this object has come out of the actual chamber, into that little side chamber. Now, what we'll notice is Archimedes' principle. Marco, read that for us, nice and loud. This is really important.
Any object completely or partially submerged in a fluid experiences an upward buoyant force equal in magnitude to the weight of the fluid displaced or.
So, what we really need to do to figure out buoyancy is calculate the weight of this. I need the weight of that right there. That's what our buoyancy is. Again, just read the actual principle. The principle says the buoyant force felt by an object is equal to the weight of the amount of fluid that has been displaced. So if you know the volume of the actual object, right, and it's fully submerged, you know the volume of the fluid displaced, but you need to figure out the weight of this fluid displaced over here. So if I want, let's write this out as a short, quick definition, right? If I want the buoyant force, that's going to be equal to the weight of the fluid. I'm going to keep going with these equal signs. The buoyant force is equal to the weight, right? Fg is weight. The weight of the fluid. Weight equals, or Fg equals, mg. The mass of the fluid times gravity. I'm putting F for fluid every time. I'm going to use F and O this chapter. O for object, F for fluid. The mass of something, in terms of its density, if I look at my formula at the top right, what's the mass equal to?
Density times volume.
Density times volume. Solve that formula in the upper right for mass. Density times volume. So replace this mass with density times volume. So it's the density of the fluid times the volume of the fluid displaced times gravity. This is your actual formula you're going to be using for buoyant force.
Is it on the formula sheet?
Take a look, actually. I don't recall. I don't remember if I put this explicitly, or if I did, but maybe.
Yeah, it is.
It is, explicit.
Yeah, PF.
Rho F, VF, GF. G, sorry.
GF.
Yeah. Rho F, VF, G. And that V is volume. So make sure that V looks like a capital V in your notes. I'll even make this a little bit bigger. It's not velocity. So the more fluid that's been displaced, listen, the more fluid that's displaced increases volume, doesn't it? So if I increase volume, I'm increasing buoyant force. So if I make the object bigger and displace even more fluid, I get more of a buoyant force. So your goal is to always, in order to get something to float, if it has a set density, you can't change its density. Maybe it's made out of steel. You can't change the density there. You need to increase the volume dramatically. If you increase this volume dramatically, you get a larger buoyant force. Why this volume? Because VF, the volume of the fluid displaced, is equal to the volume of the object if it's submerged or as it goes down further. How are we doing on time? What time is the bell today? 12:12. Let's finish with sinking versus floating on this slide. We talked about this a moment ago again, but take maybe 30 seconds. Write down some sort of a statement that describes something that would sink versus something that would float. For example, if an object sinks, it means blank. If an object floats, it means blank. And there's many answers to these. There's many ways to say it, actually. So for an object to sink, how would I fill in the missing symbol in between these two?
I don't know this is what I was going to say. An object that is dense will sink, but an object that is hollow will float.
Okay, good. You're using conceptual knowledge of it. Yeah. What else? Summer. Good. So this is for sinking, right? Now, what Cooper said is that an object that is very dense will sink, an object that is not will float. So if we want to see for something sinking, if the density of the object is greater than the density of the fluid, it also sinks. That's another way of saying sinking. And these are both the same thing, really. Okay? If the weight of the object is greater than the buoyant force, it sinks. Okay, great. Well, that's the same thing as this. If the density of the object is greater than the density of the fluid, it also sinks. And what do you expect for floating?
If G has to be smaller than FB. Yeah.
Now, we're going to put for this one, okay, this one's a little bit tricky. Fg would equal Fb for floating. Because remember that the buoyant force is a reaction. The buoyant force can't be bigger than gravity, because then it would start to rise out of the water. Imagine that, guys, for a second. Okay? You hold an object underwater, right? When the buoyant force is much greater than gravity, what happens to it? It shoots out of the water. But when it hits back on the surface, eventually it does what? It comes to rest on the surface. So if it's just sitting on the top floating, these two things are equal to each other. You're in a state of equilibrium. Now, if it's floating, it is true that the density of the object, though, must be less than or equal to the density of the fluid. It could be equal to the fluid. If it's equal to the fluid, it's kind of a weird situation. Anybody ever, and you can try this.
Yeah.
Should I do it as a bonus?
It's
Yeah.
Bonus?
Film yourself in the bathtub.
Yeah, here's
See
a
what-
bonus.
Send it to my email, Emily.
Bonus. You're terrible. Take an egg out of the fridge. Okay? You need to film yourself doing this. You can do it with a partner again, it's fine. Take an egg out of the fridge. Take a clear glass that the egg can fit in. Okay, so it's got to be clear. You got to be able to see inside the glass. A Tupperware is fine as long as the Tupperware, the egg can be fully submerged. Okay, so fill the container that's clear with water. I probably wouldn't use a Tupperware because you're going to need to add salt. You're going to have to add a ton of salt if you use a big Tupperware. I would use like a 16-ounce pint glass that you can see through. Okay, so put it at the bottom of it. Let the egg sit there. Then here's what you're going to do: add salt, add salt, add salt. But in the beginning, you might have to do it a lot. Eventually, though, you're going to see you have to start stirring it to get the solution to be like, a little bit, it'll be opaque, it'll look milky. Eventually, what will happen is this. And you have to, it's hard to get this, you got to get it right. So if you miss it, you got to do it again. At a certain instant in time, when you add the exact right amount of salt, which you could mathematically figure out actually, the egg will actually suspend in the water. It won't float, it won't sink, it'll be in equilibrium. It'll be in the case where the density of the egg object, rho O, is equal to the density of the fluid. And what will happen is this. Eventually, you keep adding salt, right, which increases the density of the water. The egg, eventually, its density isn't changing. So the egg, in a more dense fluid now, eventually will float to the top. Okay, because eventually the water will become more dense than the egg, so the egg will float up to the top. So your goal is to videotape this, but you need to try and get all three stages. The first is easy. The egg is sunk by itself. Then you add salt. Get it so that it's kind of like in between somewhere, in limbo we call it. And then keep adding more salt. You'll see it pop up to the top of the surface.
You keep stirring salt?
Okay? Yeah, I would stir the salt, regularly as you're trying to get it to the limbo stage. Once it's in limbo, if you just keep adding salt, it'll float to the top easily.
Does it have to be
You might miss that stage, so go careful. Salt water.
It has to be salt or also like sugar?
I would use salt because I think sugar might permeate the egg membrane. I think that's why they use sugar. I forget if it does or not. But salt definitely works. But you can try sugar and see.
Why can't you crush an egg if you know it?
We'll get to that. We haven't. We're going to talk about fluid pressure and pressure in general here. So we're going to get to that. I didn't give it as a bonus earlier yet, did I?
No.
That'll be another one in this chapter.
Try to crush it?
Yeah, trying to crush it.
Oh, yes.
Yeah, that's to do with Pascal's principle.
Is it because...
I think we talked about Pascal's principle at one point, didn't we? Never?
Because force on every side is pushing against it?
It's in a state of pressure equilibrium there, yeah. The force that you're applying is equally distributed to all the walls, so it's in balance. You're applying force, it's pushing back. We talked about things that are incompressible and things that were compressible. So we talked specifically about how gas can be compressed, but a solid like this desk cannot really be compressed any more than it is. some other solids like a sponge, you mentioned, a sponge can definitely be compressed, and it's a solid. So examples of variable densities. Variable means changing, right? So a dynamic density, something that's not static. A fish. Why do you suppose a fish would have a variable density?
These are gills.
And why? Like what purpose do they serve? Not how. Why?
They grow.
Again, not how, but why?
Doesn't there, does it depend on where they are in the water? Is the lower pressure greater?
Okay, so if they want to move at different heights in the water or locations, that's really the reason why. If a fish wants to move up to a surface or get away from, say, an attacker quickly, what a lot of fish will do is they'll increase the amount of air or oxygen that they get from the water that their gills are able to take, thus having their body kind of expand and they start to float. Think of like a blowfish, okay? Is that what you were saying?
Yeah.
Yeah, think of like a blowfish, it's a perfect example. If a blowfish starts to expand its size, its density goes down a lot. So it'll start to float, or raise its, depth, raise its depth. Humans have variable density. Why would you think humans have variable density? Where would that come into play? What scientific application would density come into play? What? Respiratory, okay, yeah. As you breathe, yeah, absolutely. As you're breathing, your density is absolutely changing as a whole, as an overall. But specifically in the body, different parts of your body have different densities. How might that play a role in science?
I just assume the muscular system because
It's a good example, keep going with it.
certain areas are more dense that's impacting others.
And have you ever heard like the saying, muscle is more dense than fat? It's not that it weighs more, it's more dense. So if somebody if you have, literally imagine you have twins, and one twin looks exactly the same as the other, but one twin is like pure muscle. The other twin looks just like the other twin, but not really a lot of muscle. The twin that is mainly muscle will weigh more because they have the same volume if they're the same size, assuming they're identical, except one is really mainly muscular, the other person is very just not muscular. No, not fat, same size. I mean, literally the same size, but they don't have a lot of muscle growth. So muscle growth is more dense than having some sort of like just skin on you or some sort of layer of your skin. But specifically for density, it is used a lot for things like X-rays, MRIs. It has to do with the density. So materials that are more dense respond differently. So when they are performing an MRI, they're using some sort of, not radiation, but some sort of waves that are being sent into your body. The response from them is what gives a picture of what's happening in your body. So different densities will react differently to those waves. So as a result, things like MRI machines, ever seen, what is the movie Will Smith, Pursuit of Happiness? Is that familiar? He has these machines he carries around.
Yeah.
Do you remember the movie if you've seen it? It's like a bone density scanner. It was out in like the 90s. It was before X-rays were very simple and MRIs were common.
But he was the one who was in something.
Yeah, it was in the 70s? Sorry, not in the 70s. So he would carry this device around trying to sell it to doctor's offices. And what the office did, they used the device used the density to determine whether like there was a break or something in the actual body. It's like a portable X-ray machine, not exactly X-rays, along the same lines. Liquids. Why can some liquids have some variable densities? Yeah, if you either cool or heat them. While they're still liquid though, okay, while they're still liquid, the actual density can change as a function of temperature. Same with gases, but we already mentioned that. And then an example of a hot air balloon. How would you think about that? How does a hot air balloon physically work? How does a hot air balloon work?
It fills the balloon with gas that's less dense than air.
Exactly right. Okay? You take this it's like a torch really, that's filling the balloon with hot air or a gas that's less dense than air, as Johnny mentioned. And as a result, if it's less dense than air, and the overall object, its buoyant force is greater than the weight, it will start to float. Okay, so this is the example where the buoyant force can be greater than the weight, a hot air balloon. But if you're looking at objects that are submerged in water, and the buoyant force is greater than the weight, the object will shoot out of the water and it'll land on the surface and sit there, like a volleyball holding it over the water, letting it go. But a hot air balloon, its buoyant force is actually greater than its weight, thus causing it to actually float. Okay, so when the buoyant force becomes greater than the actual weight, it floats. It's different than an airplane. And we're going to learn about an airplane in this chapter as well, but to give you a little preview, an airplane, the lift force is what exceeds the combination of the weight and the drag force, those two things. Drag force is the friction on the actual airplane, the weight is its weight. Lift force is what wings are used for. Wings are designed, they're called airfoils really, and they have flaps on them. Those flaps adjust accordingly to give the plane more or less lift. Ever notice when you're landing, look out the window, see how the flaps turn like this when you're landing? Why is that?
To cause
Slow down.
more friction.
More friction to slow it down. Exactly right. Okay? You'll see those adjustable flaps on the side with little rivets in them. You'll see them literally turn. Next time you're on a plane, look out the window when it's landing and when it's taking off. You will physically see the flaps adjusting on their own. The pilot does none of it. That's the coolest part. As a pilot today, you need to know how to fly a plane, take off, land. But while you're in the air, the plane adjusts on its own. It uses a feedback system similar to, remember the Big Bang Theory example we did the other day where it was going through that loop? That loop is literally what's going on a plane. It uses a feedback mechanism, and if the plane is tilted one way, it adjusts the flap to rebalance it. It's called system dynamics. It's a really, really interesting and prominent field in engineering. Okay, having a system that reacts on its own with no human interaction at all. That's what system dynamics are. They're called feedback loops. If you're interested in this stuff, you can research and read more about it. Let's take a look now. So example 2 here, we're going to take a look at an iron ball that's floating in a fluid. How can something like iron float in a fluid? How's that possible? If the fluid is denser, very good. If the fluid is denser, it's not water here, because iron is more dense than water, it would definitely sink in water. What is it in instead though? What is it in? Mercury. Okay, liquid mercury is extremely dense. So in this case, we're seeing here an iron ball that is floating at rest in mercury. We want to figure out how much of the ball's volume is actually floating. So physically, what do we have here? We've got an example here where the object is partially submerged. Okay, it's partially submerged. So we've got, imagine, iron is here. Let's draw iron in red. Not iron, mercury. Okay, so here's your container with mercury. The iron ball bearing, or whatever we want to call it, object is floating like so. We know that the apparent weight of it, calculate the apparent weight of it. We know the actual, the volume of the actual iron ball. We want the actual weight, we want the buoyant force, and the apparent weight. So we got several steps here, right? Several steps. How can I find the magnitude of the actual weight of this? Actual weight.
Apparent weight buoyant force.
Say again?
Apparent weight buoyant force.
So, yes, that'll work, but we don't know the apparent weight because we have to calculate those still, right? We have 3 things to do. We want the actual weight of the object, the buoyant force, and the apparent weight. I think I'll give you guys the density. That might be one. Yeah, that can help. So you do need the density, so I'll give you the density. But how would you calculate the actual weight?
Rho equals m over v, but then you have to change it.
Yeah, that's exactly right. Rho equals m over v. So let's start with that first. So let's start with the first part. Rho of the object equals the mass of the object over the volume of the object. I'm putting O's now, and I told you this yesterday. O is object, F is? For this is fluid. I heard fluid and force. Capital F is definitely force, yes. But lowercase f as a subscript you're going to see is the fluid. So the density of the fluid, the mass of the fluid, the volume of the fluid. In this case, we're looking at the object itself. All right, so we want to figure out what the actual weight of the object is. What is the actual weight of the object? So in this case, we need to get what to get the weight? How do you find the weight of anything? You need what? What do you need? The mass. If you have the mass, weight equals mass times gravity. F equals mg. We know that. Weight equals mg. So we need the mass. So let's solve for the mass first. Okay, there's the mass. The density of mercury, just in case you're wondering, we'll write that down at the top. And by wondering, I mean you need to know. So the density is 7.86. Sorry, not mercury, of iron, sorry. 7.86 times 10 to the third kilograms per cubic meter. Seven 7.86 times 10 to the third kilograms per cubic meter. We don't need the density of the fluid just yet. I'll give it to you when we do. So for now, let's go ahead and find the actual weight of the object. All I'm doing is substituting things in at this point. The weight of the object equals mg. This is from earlier in the year. If you want the mass of the object, though, we take it from this second line over here. We take this quantity, plug it in for MO. As a result, we get rho O, VOG. VO and rho O are for the object. So the density of the object, which is right here, the volume of the object, which is right here in the problem, times gravity. What do we get as a result from this one? What do we get as a result? Multiply the three quantities.
Do we have a velocity is what?
Because VO is the volume of the object. That's what I was pointing to with the arrow.
Velocity too.
Again, yeah, we're not really looking at velocity in this section at all. The objects, we're not talking about objects that are flowing underwater or moving. We're talking about volume. Okay, volume. So take that quantity, plug it on in for volume right there. Take the density right here, plug it in. That'll give you the mass. You can get a number and then multiply that by G. Or you can plug them in down here and get an explicit answer. Either way works. What do you get as a value? Let's go. Guys, check on your calculator, please. Those that don't have a calculator, take them out. Everything's in scientific notation. I see mistakes all the time on this stuff. 9.81. You got 3.85.
8.5.
I have 3.86.
Yeah, it's just rounded.
If you round, is that okay?
3.7. Well, it's definitely not. It's okay. No, it's not.
My units are newtons. Somebody Google real quick. 3.86 newtons to pounds. 3.86 newtons to pounds. See what that is. I'm just curious. What do you got? What is that in pounds?
17.74 inch pounds.
17.74 pounds?
That's Newton millimeter.
Wait, what did you want?
Sorry. 3.86 newtons
Pound.
to pound.
LB.
Put the word 2 and then LB below.
Pound is and LB.
0.8677.
But 8, so less than a pound. Okay. You did not get 3.86? That means you're off by a factor of 2, or 10 to the second, which means to me you probably messed up your exponent somewhere.
Yeah.
Times nothing.
Whenever it's off by 2 decimal spots, Marco, it's probably an exponent in one of your scientific notations that you substituted in. All right, so this is the actual weight of the ball bearing that's resting on the surface. That's the first part. Second, we want the buoyant force. We want the buoyant force up here. If I want to figure out the buoyant force, I need to think to myself, this object is floating. It is floating. So we are in a state of equilibrium. If we're in a state of equilibrium, we've got, and I'm going to scroll down so you can see this a little bit better. If we're in a state of equilibrium, here's the ball bearing. Weight is pulling down. Buoyant force is pushing up.
So they're the same.
So what are they?
The same.
Yes. Okay, very good. Same thing as Fg. This is all intuition here. This is not mathematics in this part, right? It's theory and intuition. Physically visualize what's happening. Because the ball bearing is floating, you can automatically assume that the buoyant force is the same as the gravitational force. Now, which way does the gravitational force act? Down. We don't have a negative sign there. It's okay. Use common sense, use logic at this point. Your free body diagram is what tells you that Fg really is negative. Okay? All right. The last part. Let's see. The apparent weight. What's the apparent weight? What does the ball bearing feel like it weighs? Again, no calculation needed. It's floating, guys. Thank you. 0. Remember, apparent weight is the difference between the buoyant force and the gravitational force. Well, 3.86 minus 3.86 is clearly 0. If you need to, jot it down. Whenever something is floating, the apparent weight is 0. It's got it. When you're floating, what do you feel like you weigh? Nothing. That's the whole concept of floating. Yeah?
Can you, don't they have planes that can go?
That can simulate like a free fall. They
No,
move it, you feel weightless, but you are actually moving in that case.
Oh, really? But are you above gravity or?
What you're doing is the plane is moving at the exact same rate as gravity, so you would feel like you're actually floating.
GE has one.
Not sure. I know that there are these like tunnels that have huge fans at the bottom that blow air up, and you can simulate floating like because the force of the air, the lift, is equal and opposite to your weight. They can adjust the speed, and you can actually float.
It's like a big skydive.
Sure. Yeah, it'd be like how they would train, I guess, for like skydiving or maybe even like military applications. I could see them training in something like that. It was, I think, was it Willy Wonka, the movie, right? Where they like start floating because they like eat something?
Yeah.
Yeah, it's obviously not ever possible like that, but the concept is possible. If you have enough lift force below it, it could simulate the idea of falling or like floating as you're skydiving.
Mr. Howell, what's the symbol for apparent weight? Is it FA?
What is that?
The symbol for apparent weight is FA.
Apparent weight? I don't think I even gave one. Yeah, I just have the term. So you could just say apparent weight equals Fg minus Fb.
What's the unit for apparent weight?
What's the unit for any weight? We convert it to lb from what?
Oh, is it kilograms? No.
Newtons. Remember, forces are measured in newtons. The weight of an object, listen, Marco, the weight of an object is the force acting on it.
Right.
Okay? So it's got to be newtons automatically.
Oh, yeah.
All right. Last thing for this problem. How much of this is the hardest part, guys. The other parts were easy. How much of the ball's volume is actually floating? So let's draw a little water line, or mercury line, whatever. And let's shade in the portion that we're looking for. That's the portion that we're looking for here. Now, I know the overall volume of this ball bearing. I want to find the part that is floating. I cannot find that. I will tell you now, you can't directly figure it out. But you can calculate the part that is submerged. If the whole, say the volume of the ball is 7, forget units for a minute, 7. And 3 of the volume, whatever units, are submerged. Then clearly 4 parts of it are floating, right? Volume addition postulate, like segment addition postulate, it's the same thing. So as a result, what we should figure out is the amount of the volume of the ball that is submerged. If we can figure that part out, we can subtract that from the original volume of the ball we knew to get the shaded in portion. Well, the question is, how much of the volume is submerged? What does Archimedes' principle tell us? The amount of the object submerged equals what? Good. The displacement or the rising of the water. So, how can we calculate that? Well, that means we need to figure out the volume of the fluid displaced. That's what we need. If we can figure out the volume of the fluid displaced, that is what is equal to the volume of the ball that is submerged. Because remember, whatever is submerged pushes water aside, thus displacing it. So we figure this out. As a result, we could subtract this answer from the overall volume of the ball to figure out how much is actually floating. Okay, so this is really the volume of the object submerged. I should say portion of. The portion of the volume of the object, and in parentheses, let's put submerged. That's what our goal is to figure out right now. If we can figure that out, we can subtract it and find out the volume floating. Now, we know the buoyant force. We know the gravitational force in this problem. What was the buoyant force equal to? What was the buoyant force equal to? What was it? 3.86. So, newtons, very good. So if we know the buoyant force value, what was the formula? What was the formula from buoyant force yesterday? What was the formula for buoyant force yesterday?
Actual weight minus no.
That's one of them. Yep, that's one of them. Keep going. What is it?
PFG.
Rho. Rho F.
G.
Rho F. VF.
Yeah.
G. You said PFG like 3 times. I forgot the V in the middle. Okay, rho VG. Rho VG. Yes, or the mass of the fluid times gravity. But we don't know the mass of the fluid. Listen. We are trying to figure out the volume of the fluid submerged, of the fluid displaced. So our goal is to find VF. We know G. We know FB. The density of mercury as a liquid I'm going to give you. The density of the fluid is, and I'm going to give you a table, by the way, on the test, or it'll be in the problem, one or the other. Okay, so look it up on the table or read it in the problem. The density of this fluid is 13.6. So greater than the last one, times 10 to the third. Okay? So, make sense of this before we go further. The density of the object was less than this number. That's why it's floating. Again, the density of the object was 7.86 times 10 to the third. The density of the fluid is greater than that. If the object is less dense than the fluid, it floats. So far we're good. It makes sense. We know rho F. We know G. We know FB was 3.86. Solve for VF. Solve this for VF. Make sure you put a parenthesis around your denominator. I will bet that at least 3 people will make a mistake on this calculating if they don't listen. So take a good bet to make. So take a look at the denominator here. I put a major parenthesis around it. You need to do that when you're calculating. Because the calculator will do 3.86 divided by 13.6 times 10 to the third, and then it will multiply that answer by 9.81. When in reality you want that answer really divided by 9.81. So put parentheses around your major denominator so the order of operations is preserved. I'm going to get a very small number here. You know it's going to be small because the volume of the object was very small to start.
2.9 times 10 to the negative 4. Yeah, somewhere.
Now, that's the volume of the fluid that has been pushed aside by part of the ball bearing that is submerged. The other part that is not submerged is our interest. So if the total volume of this ball bearing was 5 times 10 to the negative fifth, and the part that's submerged is 2.9 times 10 to the negative fifth, what can I do to find the part of the ball bearing that is floating? Subtract. Okay, 2.1 times 10 to the negative fifth is going to be your answer. And let's make sure we understand that. Okay, I wasn't joking when I said these problems are not easy. The next problem is going to be difficult also. We're only doing 2, that's it. Okay, they're going to be difficult problems. You need to start thinking outside the box. It's also part of the reason it's nice to have this in the end of the year so that the math, you guys are much better at these math skills. Imagine this like week 2 of physics. There's so much math involved in here, it'd be extremely complex. So you need to be certain of your math, but the theory is what's going to be difficult here too. So to find the volume floating, the total volume was 5 times 10 to the negative fifth cubic meters. minus the submerged volume of 2.9 times 10 to the negative fifth cubic meters. You see why Archimedes' principle is so important? Okay, if we didn't know that the fluid displaced is equal to the volume submerged, this 2.9 has to go here. We wouldn't be able to do this without that. Okay, so you're going to get 2.1 times 10 to the negative fifth. Forget the exponents, just subtract the numbers in your head. 5 minus 2.9 is 2.1. Carry over the exponent. Now, just to give you a little forewarning, what I will do most likely on a test for a problem like this is make this part A, B, C, D. Why do I do that, honestly? Has anyone picked up on it?
You don't screw up the whole thing.
That's part one. So if you make a mistake in part A, I allow you to correct it and continue in part B. If you use the wrong numbers from A, it doesn't matter as long as you do the work right in B, C, and D. What else? Why am I giving you A, B, C, D? I'm trying to tell you to do what?
The order is this time.
Yeah, I'm trying to tell you to do it in that order. So a problem like this, I might say to you, please determine the actual weight, the buoyant force felt, the apparent weight it feels, and finally determine how much volume is floating. Maybe even before that, I'll tell you to calculate the volume of the fluid that's been displaced because you need that number, VF, up there. Okay, all that work to get one answer at the very end. All right? This is a very simple mathematical problem when you compare it to something like a boat or things that are actually important in life, like buoys. Okay, a ball bearing in mercury has no importance whatsoever. It's taking that and extending on it, okay, or expanding on that concept. So things like buoys that are anchored down, this is not something that they don't consider. You have to calculate these forces to figure out how much tension is going to be in that chain link. Okay, so let's look at this next density that's greater than salt water and it's dropped into the ocean. It's anchored to the floor. So it's on the ocean floor. It's now anchored down with a chain. It's then inflated, causing its density to decrease to a value less than salt water. So what's it going to want to do now?
Float up.
It's going to want to float. But what happened? It was tethered down with a chain. So the chain was anchored and experienced tension in the links. What is the force of tension if the density of the object after it's inflated is 500 kilograms per cubic meter and its volume is 20 cubic meters? Now, before you start the problem, you need to know the density of salt water. It's 1025 kilograms per cubic meter. Yes. Okay, the density of water, though, you should know. It's just straight up 1,000 kilograms per cubic meter. Okay? For regular water, just 1,000 across the board. Salt water is a little bit more dense, thus 1025. All right, so we are trying to figure out the tension in the chain links. So it looks to me like we have a free body diagram coming up because I've got something that's holding it down. That's a force pulling down on the object. So draw an object. Let's go ahead and draw the weight pulling down. Let's draw a force of tension from the cable pulling down and the buoyant force pushing up. Now, if gravity is more than the buoyant force, Mullen, stop whatever you're doing and focus. I see like 3 people in the room look in your corner and laugh, and then you're going like this, so it's a little suspicious. Now, whatever else you're doing is doing. So the buoyant force is pushing up. If the buoyant force exceeds the force of gravity, like it does in this problem, it'll start to float, and you have Ft. But if the weight is more than the buoyant force, it sinks and it stays at the bottom. It doesn't have any tension in the cable. So let's go ahead and take a look at this. If it's not moving, once it starts to float, the anchors take effect, the chain has tension in it, and the object stops. This is a buoy. It's how a buoy works. So we have a net force on this. So we say the sum of the force in the y equals 0. Okay, why is it 0? Because it's not moving. It starts to float, but then it gets caught by the chain and it's in limbo in the water somewhere. So we've got FB minus FG minus FT equal to 0. Why are those two forces negative?
Because they're going down.
They're drawn down. They're pulling down on the object. So as a result here, we're trying to find Ft. Let's solve for Ft by adding it to the right-hand side. I'm going to rewrite it though. So it's FB minus FG. Similar, to our apparent weight. Because the apparent weight is what the force of tension is really counteracting in a sense. Okay, except these would be switched there for apparent weight, but similar in nature. Anyhow, let's continue the problem and figure this out. Buoyant force, what's the formula? It's in your table and we just used it in the last one. Okay? And the weight of an object is always MO times G, if we know the mass. If we know the mass. So, in this case, the density of the fluid, is that known? 1025, salt water. The volume of the fluid displaced. The volume of the fluid displaced, is that known? What is known though?
The density.
The density is known in this case. The density is known. At the very end though, what do we see? Look at the end of the problem. Okay, so we have in this case, density of the object, volume of the object. Well, use your intuition. The volume of the object, if it's fully submerged, equals the volume of the fluid displaced. Archimedes' principle. If I have a volume of 20 cubic centimeters and I jump in a pool, the pool water rises by a certain height that would be equal to a volume of 20 cubic centimeters. Because I'm literally displaced. You know what displacement means in this sense? Not displacement like projectiles, but displacement means take the place of the water. So VF is the same as the 20 here, the same as VO. So this is going to be 20 right here. This is going to be 1025. G is known. The mass of the object is not known, but the density is. Look at the red formula on the right I just wrote. Density equals mass over volume. So if I want the mass of the object, what should I replace that with? How do I solve for mass of the object in that red formula? Rho O times V. So take this V, multiply it up. So this mass right here is really rho, density of the object, times the volume of the object. So the density of the object, what was that given as? Somebody read it to me?
The density is 500.
Just 500? Okay, easy enough. The volume of the object is also 20, and we have 9.81. So it looks like if we wanted to in this problem, we could have factored these out. They'll still be effective. We could have factored out VFG and VOG as the same thing, and just seen that it's really looking at the difference of the densities, right? Everything else the same. Look at the problem, and this makes sense. If I'm fully under the water, my volume and the volume displaced has to be the same. That's 20. Gravity is the same. So the only difference here is the densities. And the density is what causes tension in the chain. Because this object is suddenly less dense than water, it wants to float, causing tension in the chain. What do you got, Julia Bonadonna?
Well, I also had a question.
Question, go.
Should I say the answer?
Yeah, no, question first, go.
Could you go about using the same formula we did to find the tension of a rope to do this? Wasn't there a formula we used?
No, there's never a direct formula for tension of anything. It's whatever forces are acting, and you just get tension by itself. Okay? Sometimes tension would then be squared over R if it was circular motion. It depends on the scenario.
Okay. And then I got 100,000.
Yes.
500?
That was 5.
Oh, 05? Sorry. Units of?
Newtons.
Newtons. Very good. Okay, this is how much tension is in the actual cable.
That was.
There are a lot of problems. I'm not going to make them all due tomorrow. So here's what you do. Tonight, problems 2 and 3. Okay? Problems 2 and 3. Now, you're over the weekend. Listen carefully.
I didn't do this.
We're gonna start 9-2 tomorrow.
That's an ad.
So you're gonna have a little bit of 9-2 work also. So you can start 1 through 5 if you have time. But I know you're busy, so at least 2 and 3 tonight.